today we are going to talk about stiction. Now what is stiction? As the name suggests that it is about sticking up some structure to its base or structure. Now let us see how a released cantilever may look like. There are two different kind of cantilevers I have drawn here. One is like here you can see this whole material is of polysilicon. Okay, so polysilicon itself is sticking to the silicon substrate. And what is the difference between this silicon and this silicon? So this substrate is like single crystal silicon, okay, and this has a particular crystal arrangement, whereas this silicon you can consider it like amorphous or polycrystalline. So here the crystal it is not a single crystal, or the crystal arrangement for the whole structure is not same. Now here the polycrystal cantilever is itself attached to the silicon substrate. Now in the second case, as you can see, this is a single crystal silicon cantilever, and in between that cantilever and the substrate, which also is a, let us say, single crystal silicon substrate, in between there is a SiO2 or silicon dioxide. Now this silicon dioxide actually acts as the anchor. So this is connected to both the silicon, like the top silicon, and also the substrate, and then this cantilever is attached here or sticked here to the substrate, and this cantilever is attached here, and then the cantilever can vibrate. Now how we can make them, that we will discuss in like in the next module while discussing about the fabrication. But for discussing the stiction, we need to know how it is coming, and for that, as I have drawn here, that before we get this cantilever there is this step where we put a let us say sacrificial layer in between the cantilever and the substrate. So there is actually, before we get this stuff, actually we have this kind of structure. So ultimately, so the process flow is actually in the opposite direction. I mean that you have first this this structure with the sacrificial layer, and in both the cases we have the same sacrificial layer, let us say SiO2, but in this case the SiO2 is not removed completely. So there is some SiO2 left at the anchor, whereas in this case SiO2 is released completely. So we have we get this kind of polycrystal silicon cantilever. Now so to release the cantilever, we need to remove this layer, then it will be like floating in the vacuum, right? So how we can do that? So for doing that, what we need to do, we need to etch or remove that layer using HF solution. HF means actually hydrofluoric acid solution. So the freestanding structure, that is our cantilever. I am writing here freestanding structure because it can be membrane also in different kind of geometry. So in this case this is a cantilever. Sacrificial layer using HF solution. So HF is hydrofluoric acid. So we call it HF solution, or also BHF or buffer HF, which is used to etch silicon dioxide, sorry. Buffer HF is used to etch SiO2. So if we have a sample with SiO2 layer on top of it, if we put it into HF solution, then the that SiO2 layer get dissolved and get removed from the sample. Then after etching that, we directly don't take out the sample from the HF solution, we actually rinse it. So then we rinse it with water, and that is not a normal water, because it has many metal ions in usual water. So we use deionized water or DI water, because if we use normal water, then those metal ions can go to your device, and that can damage the device, because that are like static charges. So we use deionized water or DI water in short. Then water is dried by evaporation. It is dried by evaporation. Now let us go back to the previous section. So what I am saying is, so you put this sample into in a BHF solution first, and then they replace the BHF solution with DI water, and then this region get removed, but there is water everywhere, because this total sample is dipped into it. Okay. So by the way, this is all are cross sectional images. So cross sectional images of the cantilever. So now you see that the water will be everywhere in the around like in the gap also, and around the gap, around the cantilever, around the sample, everywhere there will be water. Now while we start actually evaporation drying, then there will be a water droplet which will be trapped in between the cantilever and the in between the cantilever and the substrate. So there will be some water trapped in between this gap. Okay, that will form an water droplet, and because of the capillary pressure or surface tension, this will try to pull the silicon cantilever towards the substrate. Okay, so this water droplet, as it becomes smaller and smaller while drying up, so that will try to pull the cantilever towards the silicon substrate. Now if the cantilever is not stubby enough, I mean if it is long and thin, then there is a chance that it will stick to the substrate, it will get stuck to the substrate. So that is called stiction. So during drying, cantilever is pulled down to the substrate due to the capillary pressure induced by the droplet in the gap or trapped in the gap. And if the adhesion force means which is actually like pulling them together, like the while it is stuck, so the cantilever get pulled down on the substrate, then there is an adhesion force in between the cantilever and the substrate, and if that adhesion force is higher than the restoring force, because the cantilever will try to come back at its normal position. So if the adhesion force is higher than elastic force, means mechanical force, elastic restoring force, because this is the force which is trying to restore the cantilever to its normal position. The structure remain stuck. So this is called stiction. Stuck even after complete drying. Even after complete drying. Okay. Now we will see two different cases. The first case is of short cantilever. Now what happens in case of a short cantilever, which is also we can call it as stubby. This is the liquid trapped inside the gap, right, between the cantilever and the silicon substrate. Now this liquid starts to get dried up, and this happens from the tip side to the anchor side, and as you can see that slowly this liquid proceeds to the towards the anchor. Though this liquid is pulling the cantilever down, but as this is a short cantilever, the restoring force is also much higher than the like the surface tension, the capillary force. So because of that, it is not able to pull it down so much that it will get stuck here. Rather, the liquid starts drying up and it will ultimately get completely dried without even pulling, without any stiction. So if the beam is stiff, then the cantilever will not bend much, and no stiction. No stiction. Now let us take these two cases where we are taking a longer beam, much longer and thinner beam, and we have two different widths. Okay, we have two different widths. So we will see that how the drying happens for these two beam. So, as you can see, as it starts to get drying up, then it forms a kind of neck here. So, in between the tip and the anchor, towards mostly towards the anchor, it forms a neck like this. So, this because of this neck, the water droplet actually gets separated. So, one water droplet forms at the towards the tip side and one water droplet forms at the like the anchor side. Now, that anchor side droplet get dried up, and this has the cantilever is very steep here at the near the anchor, right. So, it will not be able to pull the cantilever down, but the tip side water droplet here, the force required is much smaller than the force required here. So, this water droplet actually will be able to pull the cantilever down, and then it can get stuck towards the to the substrate. And as you can see here, this droplet, how much will be the area of the droplet, that also depends on the width, because this is ultimately width square. So, W1 square or W2 square, and so the it will be almost, because it usually the droplets starts to form in spherical shape, and then it will try to take the shape of the cantilever symmetrically. So, it will be almost like square shape, and then it will depend on the width of the cantilever, that how much will be the contact area, and on that contact area actually the adhesion force also is dependent. So, while drying, it's near the anchor of the cantilever. Trapped water droplet breaks into two. Droplet at the tip pull down the and that beam will bend and get stuck to the substrate. Okay. So, this trapped water droplet near the tip will actually pull down the cantilever to bend, and stiction will happen. So, here I am showing one of the ACM image of a stuck beam. So, here you can see that the anchor side, it is you can see the shadow where it is like there is a gap in between the cantilever and the substrate, but at the tip side it is stuck. So, it is like stuck to the substrate. So, that is why you cannot see any shadow. So, this is one of the real image of a stuck beam, and if you see it cross section wise, then how will it look? So, let us say this is the substrate, and then you have the anchor here. Here it will be not be stuck, but then at the tip side it will try to come down. Okay. Now, what is stiction? Actually, by name it does mean that static friction. So, friction force we are all aware of, and this is kind of static friction force. Now, what can be of different reason for stiction? So, one is release stiction. So, that we have already discussed, right, while drying after etching the sacrificial layer. After etching the sacrificial layer, then during evaporation drying, while we are evaporating the water, right. So, during evaporation drying, stiction can happen. Another type of reason may be in use stiction. So, in use stiction, let's say you have a now released cantilever. Now it is vibrating, right? It is always like your application is such that it needs to vibrate. Now, while we are electrostatically vibrating on cantilever, let's say somewhere we apply some higher voltage, and because of that it gets pulled in more than the critical gap what it should not be, right. So, if it is more than that, and if it once it touches the substrate, then in that case if the adhesion forces are higher than the restoring force, like more than, let us say, pull in voltage, the more than the pull in voltage the voltage is applied, then once it contact the substrate, if the adhesion forces are higher than the restoring force, then it can get stuck. So, this can happen during because of some higher voltage also, or let us say it suddenly have some kind of shock and then it gets stuck to the substrate. So, that is also possible. So, that can be because of mechanical shock, then voltage applied, more than Vp means V pull in, more than pull in voltage. If we apply more than pull in voltage, if we apply voltage, then also it can happen. And what we need to understand in this context is the stiction is a measure failure mechanism in microfabrication. this is a major failure mechanism in microfabrication. Now the question is that how we can avoid or overcome stiction. So during release mostly, because in use is we have to be careful, we should not give any mechanical shock, or we should not put more more voltage, that we need to be taken care of. But during release, how we can get rid of, because this is an unavoidable situation, right? While we are making this kind of devices, we need to go through that sacrificial air leaching and then washing the sample with water and then drying the water. So we need to do that. But how, what kind of strategy we can take so that the stiction will not happen? So one is use, one point is use low surface tension material. Low surface tension liquid like methanol. So if we, other than water, if we use actually in the final step, if we use methanol to wash it, then the chances of stiction will be lesser, because ultimately the water droplet is what it is pulling the cantilever down, right? But if it is methanol droplet in place of water, then what will happen? The pulling force will be lesser, because the surface tension of methanol is lesser than water. So it will pull with lesser amount of force. Another option is provide narrow dimples or anti-stiction tips. So what is that? Let's say this is the, as I was drawing, so this is the substrate, and on top of that you have the cantilever. And then here near the tip or so, you can put some narrow dimples or anti-stiction tips. So even if it gets pulled in, the contact area will be very less, because this is just like anti-stiction tips. So very sharp tips, so the contact area will be lesser, and the adhesion force will be never higher than the restoring force. So it will not get permanently stuck to the substrate. Other two techniques are supercritical drying. So sublimation and supercritical drying are two different techniques where we do not form actually liquid gas interface, because in sublimation actually the solid material itself directly evaporates without going through the liquid phase. And supercritical drying also is similar technique where we have some kind of liquid going to gas phase directly without going to the vapor phase. So we will discuss about sublimation and supercritical drying later in a little bit of detail. Let us talk about different kind of drying technique. So this is called phase diagram. Many of you are already aware of that. So there is this pressure and temperature, and depending on different pressure and temperature, what will be the phase of the material, like whether it will be in solid phase, liquid phase or vapor phase, right? So as you can see that as you are increasing the temperature, it is going from solid phase to liquid to vapor, and that is the usual like you are familiar with this phenomena, right? While you heat up the ice, it becomes water, and then you heat up the water, it becomes vapor. Now, usual drying technique or the evaporation drying technique goes from solid to liquid to vapor. So, you have solid, then it goes to liquid, and then it goes to vapor. So this is evaporation. And in this case, the usual technique, the water is in liquid phase. So it is in liquid phase and it goes to evaporation, it goes to vapor phase by evaporation, just by heating it, or like the normal evaporation. As I was discussing the sublimation, there are these materials which can go from solid phase to vapor phase directly. So all this phase is vapor phase. So sublimation happens from solid phase to vapor phase directly without going to the liquid. Okay. So there is no formation of liquid or liquid droplet or no surface tension at the liquid air interface. So stiction will not happen there. So there is certain pressure and temperature above which the material can be considered, or the fluid can be considered as gas. So above this point, that is at some particular pressure and temperature which is called critical point, the fluid will be uh, called gas. And what is the difference between a gas and vapor? So there is this property that if we apply higher and higher pressure, then the vapor can be again converted into liquid, but a gas cannot be. So gas and vapor are two different kind of phases. Now there is some technique called supercritical drying, where from the liquid phase, by going into higher temperature and pressure, it can go to the gas phase above the, can go over the critical point. So we increase the pressure, we increase the temperature, we increase the pressure, then we increase the temperature, and then again we decrease the pressure to come back to the vapor phase. So we totally avoid the liquid vapor interface. So this is called supercritical drying. Now for sublimation, we can use tertiary butyl alcohol, or it is called T-butyl alcohol. And supercritical drying can happen with CO2. So sublimation drying, how we do? We, after DI water, we replace the DI water with methanol. Anyway, it has low surface tension. Then we replace the methanol with this tertiary butyl alcohol, T-butyl alcohol. And this is in liquid phase above 26 degree centigrade. So it melts at 26 degree centigrade, and we put liquid tertiary butyl alcohol. So this is liquid, and then we refrigerate it, means we put it in a freezer. solidify. So you solidify it inside a freezer and then it will sublimate. So in this step there is a solid tertiary butyl alcohol or T-butyl alcohol in the gap. So as I was saying that this is a substrate and then on top we have the cantilever, and in between the gap this is the region where the water was forming droplet. Now this is T-butyl alcohol, solid T-butyl alcohol, and that automatically evaporates like from the solid phase itself. It evaporates to the vapor phase. So we do not have any liquid droplet forming or no stiction. And another option or another material we can use is p-dichlorobenzene. This also can sublimate. And for that we need to use 56 degree centigrade, like it melts above 56 degree centigrade. Tm, melting temperature. Now for CO2, like supercritical drying, we do it liquid CO2. So again let us draw the pressure temperature diagram. So this is pressure and this is temperature, and then we have this graph. So let us say this is the critical point. Okay, this is solid, this is liquid, this is vapor, and above the critical point it is gas. So and for CO2 this point, this critical point is somewhere at 1073 psi. This is 31.1 degree centigrade. So what we do is first we take the CO2 in normal temperature and pressure and then apply high pressure to make it high pressure. So it will be at high pressure liquid, and then we apply high temperature also to go over the critical point, and then again it comes back to vapor phase. Okay. After DI water, so the sample was in DI water, that we replaced by methanol initially. Methanol, so that is that low surface tension liquid, and then this is replaced by liquid CO2. Liquid CO2 at 1200 psi and 25 degree centigrade. So it is at 25 degree centigrade and 1200 psi. Okay. So this point is this is 1200. So this was 1073, which is its critical pressure and temperature, and this is, we go above that pressure wise, this is 1200, and this temperature may be about let us say 25 degree centigrade, and then we increase the temperature to 35 degree centigrade. Heat to 35 degree centigrade to make it gas. And it actually exits as gas without forming liquid droplet. So, as we have seen now that we have used here CO2, right, liquid CO2, because it has like critical pressure and temperature is in our reachable domain, like it is 31 degree centigrade and 1200 psi means about, let's say, so we are using here CO2 because its critical temperature and pressure we can achieve easily. Temperature, critical temperature is 31 degree centigrade, we can definitely go above that, and 1200 psi means about 73 atm pressure, we can also achieve that. So liquid CO2 is used, but there are other materials also, so that we will now discuss. Like, so if I, this is, let's say, TC and this is PC. So this is critical temperature and critical pressure, and let's say if we take different material like different gas, let's say hydrogen is about minus 234.5, and this is in degree centigrade, this is in PSI, it's 294. Okay, then O2 is minus 118 and 735. N2 is minus 146 and 485. CO2 is plus 31.1 1072. Then we have carbon monoxide also, like plus 141, 528, and water is plus 374 and 3212. So you see here CO2 is most achievable because the temperature is almost in the our room temperature region, whereas for the other, all the other cases it is either very high or very low, so which is difficult for us to get, because initially we have to start below critical point, right, because we need liquid CO2, like that we need here, we need liquid night N2. Liquid N2 also can be used, and it is very frequently used for different purposes, but here liquid CO2 is more preferred.